Okay, so for this question, we need to design a low-pass filter. So what we really want is a low-pass filter with a cutoff frequency at 10 Hertz. Okay, low-pass filter. So that's the one we want. So we are gonna look at second order filter. Okay. So it means there are 2 poles and 2 zeros. So the poles can be somewhere here, for example, and 0 can be somewhere here. Okay, so you need to know that the Hz, by definition, equal to Z minus 0, number 1 maybe, and Z minus another 0, okay, divided by a Z minus a pole. That's the definition of the zeros and poles. Okay, poles makes the denominator zeros. Okay, so if based on this definition, you will see that for any frequency, so we're going to examine the frequency around the unit circle. Okay, from here, that's the 0, and we go here, we go this way, and this one is half pi, and we got a pi, and we'll go all the way back to a 2 pi, okay, to the same position. Okay, and at any position, so you can see if Z equals to here, for example, we start here, and Z, this position minus the location of 0, okay, so you can write like that. So Z also equals to the distance to zeros, okay, because you minus those zeros. Okay, distance to zeros is this. Okay, it's pretty large. Okay, and divided by the distance to poles. Okay, so the poles is the closest here. So at this position, as a beginning point, when the frequency equal to 0, we got the maximum amplitude. Okay, so you can imagine when we keep moving along here. So for example, we are here. Okay, we are here. So the zeros is here, 0 is here, and the poles distance is here. Okay, so it's not as big as the beginning, so kind of drop. And when we reach here, half pi, you can see the distance to the 0, we are step on the same location as 0. So the distance to 0 for one term is 0. Okay, for another term is max, but this is a multiplication, so the distance to 0 got 0. Okay, and to the pole is max, so the total is 0. So when we reach half pi, we got 0. Okay, and if you keep going this way, and you will reach to the max again at pi. You're gonna reach that one, and if you keep going, and you got that one, you keep going to a 2 pi, you reach to a maximum again. All right, so this is the curve or the shape of frequency domain by looking at Z domain. So this is a rough methods to sketch this frequency domain by looking at the location. Okay, so if you change the location of the poles and zeros, you do this analyze again, you can roughly, find out the shape. We're going to do the simulation in the end of this video to see the location, the placements of those poles and zeros. Okay, so if we know that, we're going to examine something else. First, we want to define, we want to find out how much the cutoff frequency, sampling frequency should be. Okay, the sampling frequency. So we know our signal is between 0 and 125. So double that frequency at least, we need a 250 hertz sampling frequency. If that's the case, that actually means here is 250 hertz. Okay, so if you go around is 250 hertz, and here is 1/4 of that. That's only, how much is that? 62.5. Right? Let me have a look. Yes, that's only 62.5. That's not good, because up to 125, you all have those useful information. You want to cut it at a 10, but you don't want those information pass. Okay, if you have a filter look like this, you will, allow the some information pass. That's not good. So we can try to double that, so make it 500 hertz. If that's 500 hertz, then this one is 125, okay, which is good. Okay, let me draw that again. So if that's the case, we're gonna have this 125 hertz, okay, and which can satisfy our requirements. Okay. Okay, so we know the sampling frequency now. Then we want to find the position or location of the pole. Okay, there are some parameter we need to calculate. For example, R, so which is the distance or the length of this one, is at the pole is equals to 1 minus the bandwidth divided by the cutoff sampling frequency, and multiply with a pi. Okay, so here I will see the cutoff frequency is 10 hertz, so the bandwidth here I will use 10 hertz, and divided by 500, multiply with a pi, and what I got is 0.937. Okay, so we can fill in the blanks. Now we know zeros are at real term is 0, it's at a unit circle, so this is actually J, right? So the location of those zeros or the poles can be write as a polar form, can be write like a R and theta form. Okay, for the poles, the angle is 0, right? And the R, we just got it, R equal to 0.937. Okay, for zeros, we got the angle is, one is 90 degree, right? One is half pi, another is negative half pi. Okay, you can see that this one, if you see this one, half pi, and the R is just 1 unit circle, right? It's at the unit circle. So we can write that the expression for the domain, this filter is z minus e to the order of j theta, okay, the angle. Okay, so for the first pole and second pole, okay, we can write like that way. I will just directly give you the form. So this one, the first one is half pi, angle, the magnitude is 1, so I'm just not writing it. So another one, e to the j negative pi over 2, okay, divided by z minus e there is a magnitude 0.937 e to the order of j 0. Okay, both are 0, so 0 is just 1, right? So another one, just directly write that that number. Okay, and you can also see this one. This one is the positive j, this one is the negative j. Okay, so so hz just equal to z minus and plus j, so it's z square minus j square, right? So j square is -1. So for the bottom we got what was that? The angle for the pole, for the pole is 0 and pi, right? So I shouldn't you know, skip steps. I shouldn't skip steps. So this one is minus e to the order of j pi. Okay, so shouldn't skip any steps. So this one is 1, this one is -1. Okay, so on the bottom is z minus 0.937 multiplied with z plus 0.937. Okay, and we got the final result is z squared plus 1, okay, over z squared minus 0.37 squared. Okay, and we can further clean the term to make it divided by z squared up and down, so this become 1 plus z to the order of -2 minus 1 minus 0.937 squared multiplied with a z to the order of -2. Okay, so that number is, let me use a calculator. This equals to around 0.87. Okay, so we can directly write the difference equation. So the difference equation is look like this. So this multiplied to the other side, you can see this one gonna equal to hz minus 0.87 hz z to the order -2. This side is 1 plus z -2. Okay, if do inverse Laplace transform, there's going to be lowercase h, right? Lowercase h is the impulse response, so we can just write the output sample for yn, so it's a time domain now, minus a 0.87. We know that this is a time domain delay. Okay, so delay by 2 units, and this one becomes xn, and this is x delayed by n units. Okay, alright, so we can keep move terms. We got yn equals to positive yn minus 2 plus xn minus 2. Okay, so we need to draw the diagram as well. So we start with a xn. Okay, is go into a delay unit twice, so to generate this term. Okay, So this is the xn minus 2 term, and it will also get the xn term directly here. Okay, so xn term plus that term, you're gonna equals to a yn term. So this yn term will go into a delay unit as well, twice. Okay, it's delay units. Need to go down a little bit, and this term is the yn minus 2 term, and it's gonna multiply something. Okay, gonna multiply 0.87, and I will put this one back. Okay, so that's this term add to these other 2 terms, so 3 term A together equal to yn. Okay, just shrink everything so you can see a bit like a full screen of everything. Alright, so next I want to quickly show you a something. So here is a tour from a website called DSP First. Okay, this is a very good textbook as well. It provides a lot of demonstration you can play with. For example, this pole and zero placement. Okay, you can double click that, and you can download the thing, the whole package. There are a lot of useful tour, visualization tour. You can download the package from here and follow the instruction. Here's the instruction. You can install that, so we can play with it. So here is something we had. So let's play the pose. So pose was at 0.96. Okay, at both sides. And we'll put 1 here and 1 here. Come on. Okay, got a 2 pose. I want to have 2 zeros. I can click is this one, 2 zeros like this. So you can see that's a that's the spark-chrome frequency response. Look like this. Okay, it will end it at this point. So if we change this locations, for example, if we delay them all, you can see we can put the pole, for example, vertically. Okay, can put another pole here, and we can put another 0. We can put 0 here, another 0 here, second order. So you can see is a band pass filter. Okay, and the angle of this 2 pole, you can see the angle of that 2 pole gonna affect the center frequency. You can see if you go this way, smaller, you will see this center frequency close to 0. Let me keep going. Okay, you can see it's keep to 0. But if you put this one to the other side, and the angle to a negative angle, so you can see it's go close to pi. All right, and that's the angle, and if you put this one far away from the origin, that means the r, the length of this vector, will affecting the bandwidth. Okay, so see if you want a larger bandwidth, so this one give you larger bandwidth. Okay, so you can play with this one, so you can see you can get a lot of insights about how to place pole and zero. And after you design, you find it satisfy, you put the location of pole and zero into here. Okay, into into this equation, then we can find the parameters for the IIR filter. Okay, so that's it.